Okay, so in the last video, we determined that we were going to have different types of behavior at J, K, and L. For all of these, our first eigenvalue we knew was a negative number. I don't have to write equals negative, I can just write less than 0. I'm a math teacher, I know how to do that. Okay, and so we were looking at the second eigenvalue to try to see what sign that was going to be, or if it was going to be 0. So if I'm at point J, notice point J, that corresponds to where t is negative, but d is positive. So that tells me that lambda 2 is less than 0 as well. So that would mean I would have 2 negative eigenvalues. So all of my straight line solutions would be approaching the origin. And of course, my solutions would start roughly parallel to one and end asymptotic to the other. So my phase portrait would look something like this. Again, without knowing what the eigenvectors and eigenvalues actually are, I don't know which straight line solution dominates as t goes to infinity and negative infinity. But that's a representative solution curve, and there the origin is a sink. I'm going to jump down to L next, so we've dealt with that one. Let's deal with L. If I'm looking at L, this is where D is negative. Okay. So now we've got that lambda 2 is positive, but in this case when T is negative, we know that lambda 1 is going to be negative. So we've got one of each. So I'm going to have one set of straight line solutions that approaches the origin and one that goes away, and that's my familiar saddle. So at L, we have a saddle. Now if you look back, that's also what we had at I. So I've got the same sort of thing at these 2 points. If I also have the same sort of thing here, then the entire region below the t-axis is one region where I have saddles. Okay, we're going to have to come back and take a look at that in a moment. Let's do K first, because that's our last one to look at. So K was the point we had where D was equal to 0. So we saw that if D was equal to 0, our second eigenvalue was going to be 0. So we're going to have one line of equilibrium solutions and one negative eigenvalue, so that my other solutions will be straight line solutions, but that are approaching an equilibrium solution, not necessarily the origin. And again, when the equilibrium solution isn't unique, we don't bother to classify the origin. All right, so now let's just take a look at the one place we haven't looked at. What if we're here so that t is 0 and d is negative? Okay. All right, if that's the case, my eigenvalues are going to be 0 plus or minus the square root of 0 minus 4d over 2. Of course, if d is negative, negative 4d is positive. So I'm getting plus or minus a positive number over 2. So I'm going to be getting one positive and one negative eigenvalue. Anytime I have that, that's going to give me a saddle. 2, 2, 2, 2. Okay. So if I were to add a point here, JKL, this would be M, all of these points are saddles. Okay. So I got them by looking at them as 3 different cases, but what I see is that it's only the positive d-axis that should be drawn in pink, because only that is a boundary between one type of behavior and a different type of behavior. Everything below the t-axis is a saddle, regardless of which side of the d-axis it's on or whether it's even on the d-axis. So the 3 curves that break up different types of behavior are the t-axis, the positive d-axis, and this lovely and beautiful parabola, which was t squared minus 4d equals 0. That is our trace determinant plane.